Well, hello, this is Eric Topol for Medscape One-on-One, and I'm really delighted to have the chance to have a conversation with Professor Eddie Holmes from the University of Sydney, one of the world's great evolutionary virologists. So welcome, Eddie.
Thank you, Eric. It's a real pleasure to be here.
Well, we have plenty to talk about, obviously, with the SARS-CoV-2 being like the only thing going on in the world. Well, before we do, how are things in Australia right now?
Good. And so Australia, because we are an isolated island, which has made things somewhat easier, obviously. So Australia, back in late January, instigated a flight ban with China, travel ban with China, and that actually helped a lot, and it delayed the importation of the virus really until late February. Then we had an outbreak. The first wave came in sort of March and ended in kind of May. And then a second wave came into Melbourne in July. I live in Sydney, and we didn't really get the second wave. So then the second wave was quite bad in Melbourne. They had quite a serious lockdown, and they've now, some weeks ago, they've now crunched that. So they've had no cases there for 50 plus days. In Sydney, just to put it in perspective, and I think your listeners may be shocked by this, we've had maybe a bit over 4,500 cases in total in Sydney, in New South Wales, for the entire pandemic. And our mortality number is something like 60 cases. And many of those people have been in hotel quarantine. So if you do close your borders and you do clamp down hard, you really can control this. At the moment, we've got a small outbreak, hopefully a small outbreak going on in northern Sydney. And we had something like 8 cases yesterday. So again, that's a quarantine. You can close your borders, but occasionally things get through quarantine. This appears to have got in. Hopefully that they will control that. But it's a very, very different picture here than you're seeing in many countries.
Are you able to proceed as pre-pandemic?
Oh yeah,
yeah, which is
totally.
wonderful.
So we had we were in lockdown in March and April. My university kind of reopened in May, and so we've been open and working since May. And we had basically no cases for weeks and weeks and weeks and weeks in New South Wales, and just recently we got a small outbreak, and the suburb where it's they're in lockdown, but the rest of Sydney is not. So there are some restrictions. So it's not pre-COVID, but it's certainly a very different landscape here than you see in many countries.
Right. No, we're envious, as you can imagine. Now, before we get into what happened in January, you've been studying lots of different RNA viruses throughout your career. So can you just give a bit of background about kind of what was going on in your priors before coming to this one?
My priors. Yeah, so I've been doing this for 30 years now, and I started off like many people did on HIV, because that was the virus that introduced us all to emerging viruses. And I was living in Edinburgh, and I was working on the kind of outbreak in Edinburgh that was largely associated with injecting drug use. So that was back in the early 90s. Then I moved to Oxford, and I started doing more kind of comparative evolutionary virology, looking at how different viruses evolve, what are the common principles underlining virus evolution and emergence. And in the last sort of decade or so, I've mainly been doing metagenomics to understand, if you take how big is the virus sphere, what structures the virus sphere, okay? And the way I answer that, and how do things move, viruses move between species. And the way I do that is by doing this metagenomic sequencing. So and it's normally animals, so taking animals, what virus do they have? And what shape, it's looking at whole ecosystems and what's moved between them. And a lot of that work has been done in collaboration with Professor Zhang, who I'm sure we'll talk about shortly he was in Beijing, now in Shanghai. And so we together have done a lot of metagenomic sequencing. And it was that technique, in fact, that they used to sequence SARS-CoV-2.
Right. So that's a really important point you're getting at, which is this next generation sequencing, where you can sequence everything approach and then figure out what it all is.
So
that's been transformative, right? I mean, that's changed the whole.
Incredible. Yeah, just in terms of pattern discovery, think back to HIV. So it took two years from the first description of AIDS until we found the causative virus. Okay, and that was done using classic virological techniques. SARS 1 took a few weeks. As we'll discuss, Zhang, it took 40 hours to get from the sequence samples arriving in his lab to getting the virus. Okay, so that I mean, there's lots of failings in our approach to emerging diseases, huge failings, but pathogen identification is not one of them. Okay,
right.
That is something we can do, and the genomics in this outbreak has been absolutely astonishing. We've got over 250,000 genomes sequenced. We may well get 1 million by the end of the outbreak. So that bit has been good.
Yeah, no, I think it's changed the world in terms of the reliance on genomics to understand spatial temporally what's going on in an outbreak and so much more. Now, the first documented case in December of COVID, and I guess the samples arrived to Professor Zhang's Shanghai lab on the 3rd of January. And he, as you said, 40 hours later had this sequenced. And then there was, I guess he was submitting this to Nature, the sequence, which was great. And you and he have collaborated quite a bit over the years. And you suggested it would be good for him to put it out on the web somewhere, right? So everybody could start working on it.
Yeah. So what happened? Yeah. So what happened was we actually had. I'll just replay a bit. We had 7 samples. Well, Zhang had 7 samples arrive in his lab on the 3rd. Of those, and they were all associated with this famous seafood market in Wuhan. Workers there or people who live right next door. Of those 7, one, they're all lung wash samples. We actually had a lung wash study project going on in Wuhan at the time.
Wow.
Right. Yeah, of those 7, one of the lung wash samples was positive on January the 3rd. He sequenced it on the 5th. On the same day, it's actually very important. He sent it to GenBank. But more importantly, he told the Ministry of Health in China that it was obviously a novel coronavirus. It was clearly very closely related to the first SARS virus. In fact, between us, we were calling it SARS, right? It's kind of obvious at the time it looked that so close. And because of that, because it was a coronavirus, because the first SARS coronavirus was respiratory, we thought this is going to be a respiratory virus. We said this is likely respiratory, and that people should take precautions. So that was made apparent very early on. Then as the week, I was angling for, and I should, before I get to answer that question, you got to remember this is the first week of January, and so it's a very different picture than we are now. So at that point, it was, we had 20 odd cases maybe. It wasn't, it didn't, you couldn't at that point say this is going to be a global pandemic that's going to completely affect our lives.
Right.
It wasn't like that the first week of January. It was like, hey, this is a really interesting outbreak. And the case numbers were not that high at that point, and it suddenly kind of increased. At that point, it was quite low. And so I thought, okay, it'd be great to put this out there. And most people in the world hadn't even noticed what was going on. And so over the week, I was encouraging to do that, but there was I got to be careful what I say here, but there was some pressure in China not to publish anything at all, and I think the Chinese authorities wanted to keep a lid on what was going on, and so he was obviously I'm in the West, it's a bit different, but he in China was under some pressure not to release too much data, and then I think it was on the 8th, the Wall Street Journal of all places published an article saying it's a novel coronavirus, because clearly they had heard from other scientists in China that it was. And there were other groups sequencing. Okay, so there are many people working on this.
Okay.
Zhang was not the only one, nor even the first one. But it turned out we were the one that made open access.
Right.
So on the 8th, I think the Wall Street. So we submitted a paper on the 7th to Nature. Nature were very keen for us to release it. Wall Street Journal announced it on the 8th. On the 9th, I think the Chinese authorities confirmed it was a novel coronavirus. Okay. And at that point, it just seemed to me quite ridiculous. Here everyone knows it's a coronavirus, but we're not saying what it is. And of course, as the week was going on, the cases were slowly increasing. It became more and more of an issue. And then there was a lot of social media people, discussing it's a coronavirus. We need to know what it is. And Jeremy Farrar, director of the Wellcome Trust, certainly was very vocal in that. And I was trying to encouraging Zhang to do this. And again, he was under some constraints. And then it got to the point I thought we have to get this out now. She's just crazy. And so I called him. It was very early Saturday morning my time, even earlier his time, I should say. And he was on a plane. He was about to fly between Shanghai and Beijing. I can never remember which direction he was going, but he was strapped in his seat, And I was saying, Zhang, we have to release the sequence. And he said, "Oh, give me a minute to think about it." He said, "Okay, do it." And so then, luckily, my good friend and colleague Andrew Ramber from Edinburgh was still awake. It's like 1 a.m. in his time, and he runs this website called Virological.org, which has been a very nice open access forum. And we had some frantic emails, and then we wrote some text. So he helped me do this, write some text for the release, and then I posted it on that website Saturday lunchtime here. And then simultaneously put it on Twitter. And that was the first, that was the open access moment for the.
It's going to go down in history as one of the most famous tweets ever.
Yeah, I'm not very good at Twitter, Eric, right? So I tend to use as few words as possible.
It's actually pretty remarkable. And in fact, in Nature, Professor Zhang is one of the top 10 of 2020. And the story that you just recounted is in there where you were on the phone with him and the flight attendant was telling him to get off the phone and he was telling you go ahead and put out the sequence. And, it's really historic because obviously every minute counts when you're trying to move forward. And the key here is that it went to the NIH and Moderna very quickly.
Yep.
In fact, what's interesting is to hear how it was just a matter of hours before they started rolling from that sequence to the vaccine. Did you envision that was the next step, the vaccine?
No, that's happened so quickly. And I knew there would be, I thought what's the first thing people will do is they'll use it for design, PCR tests. And I thought that's the obvious thing. And that's what Christian Drosten and Marion Cooper's people did in Europe, which was very good. The vaccine thing, the whole mRNA vaccine, that's a completely, I didn't see that coming. And that is incredibly, and that is a complete game changer, and it's so gratifying. But I can also say it was actually quite tense in all this, send these sequencing and editing things. And I felt under such pressure to get it out. I didn't even check what it was before I posted it. Okay, I got the sequence file and I thought, right, I'm going to put it up there. And then after I posted it, I thought, actually, I better check that it really is a coronavirus. So I quickly did a quick bit of blasting, and it really was the right coronavirus. I thought, God, I could have put completely the wrong thing up and gone down in history as one of the stupidest tweets ever. But luckily, it was the right thing.
I don't think so. It basically accelerated the whole process. And I think the fact that we have the vaccines, 2 of them out, mRNA, based on that sequence now, is quite remarkable. Now, I don't want to get into the details, although it's been written about that there certainly was pressure on Professor Zhang with respect to the rectification order and some lab issues. There's obviously his side of the story and whatnot, but it wasn't easy. That is, it was great for moving the field forward, but he may have suffered in part because of his open science approach, I guess.
Yeah, and again, I need to be cautious here because there are people, there are people's lives and not lives, but people's careers that are involved in this. So I need to be careful what I say. So, there were pressure, and that there were some consequences for what we did. But I don't think I don't regret. I'm sure, and I know James and Grant regret for microseconds what we did, and I do it a heartbeat now. We had to do it. It was a moral, scientific imperative for us to do it. And I think it shows, just shows, as you said, because of the amazingly rapid development of vaccines based on that sequence, it shows the absolute power and necessity and beauty of open science. Okay, and I think that that's a critical
Absolutely.
thing. And
Yeah.
I hope that once our present political issues change, and I hope they'll change in January, that the authorities in China will realize how important open science really is. Okay.
Right.
And
Well,
I think they wanted to. I think the word SARS is quite a difficult thing in China, and I think they really didn't want to panic people, and they wanted to control the message, and that was their goal. But it kind of probably stretched too far. I think that's the issue.
right. Well, in that nature recognition of Professor Zhang, he's quoted saying it was a turning point for China. It was a turning point for the world.
Yeah.
And clearly, Eddie, your role in this was damn important because, you helped get it out there, and we're indebted to you. I just want to say
Yeah.
we're really indebted to you.
Well, I think I'm just a messenger. Look, I've worked for China for many years. I understand how a little bit how China works. And they have a lot of pride, and they there's a lot of national pride, and you just have to be wary of the way you do things and behave in certain ways. But I am the only Western scientist involved in a lot of those early papers, because I spent a lot of time going to China and working them. And when you go to China, you're working with scientists, right? You're not working with the state apparatus.
Right,
people need to
right.
understand that. It's just like you and I talking now. You're with these people, and it's just a normal scientific interaction. They happen to be Chinese. You're in China. That's the only difference. But everything else works the same way. And I think the critical thing is, this is what really worries me most of all. If the politics gets in the way of data sharing and the science, we are in a much worse place than we will be. And the key thing now is we have to try and prevent this ever happening again. And step number one has to be immediate, rapid, open data sharing. You've seen how the speed is of the essence when it comes to a pandemic. And any barrier that gets in the way of us sharing that data, because there's political consequences of that's going to make us a world a much less safe place. Absolutely. So we have to work with these people. We have to share data as openly as possible, and that should be the lesson you get from this outbreak.
No, that is so important to reinforce. And as you say, it wasn't just to develop a vaccine, which you could hardly envision could move at this unprecedented velocity, but also diagnostic testing. So there was so much at stake there. Now, fast forward, now we have these two vaccines based upon that knowledge of the sequence, with the 2 proline substitution in those both to help stabilize that to get maximal antibody production. That was a nice tweak, which is kind of historic too.
Beautifully done.
Yeah, no, it's kind of amazing. Andrew Ward, who's a colleague of mine here at Scripps, as well as McClellan and many others, participated in that. But now we have a new problem. Mm-hmm. Not that we've got this virus squashed in any respect outside of countries like yours, continents like yours. But this variant in the UK, not necessarily born in the UK, but this B117 has cropped up in recent weeks and has led to a big surge and spread in not just parts of the UK, but it's been recognized. I understand there's at least one case in Australia, Netherlands, Italy, Denmark. So it's gotten around a bit, and obviously there may be other countries that aren't doing sequencing that may have it there. And in the US, we haven't seen that yet, or the South African variant, the N501Y, which seems to have some thread as far as an important spike mutation. So what's your sense about this? Where are we headed now?
Yeah, no, it's obviously the question of the moment. So I'm not directly involved in the UK work, so I'm seeing it kind of secondhand. But from the body of data that I've seen, there are definitely concerns here. I think there are a number of things that are kind of acting, that there's all the links in the chain. So you start with the epi, as you've mentioned. This variant does appear to be growing very rapidly in the UK. And that's not just because I think the south of England had freer restrictions, because if that was the case, then all the variants would increase in frequency. It's one particular one, that's one lineage that's increasing in variance compared to any others, and it's growing quite quickly. And the same appears to be true in South Africa. It's a different lineage, but it has some of at least one of the same mutations. So that's a worry. The second is they're reporting now that the virus has evidence that has higher viral loads of infection, measured by lower on average CT values and more sequence reads when you do sequencing. So they're saying there's more virus. Of course, that would explain the faster growth rate. And then if you actually bore down to the actual biology of the virus, as you mentioned, there's this mutation at amino acid 501 in the spike protein, which is in the receptor binding domain, which is one that we'd already flagged as being a really key site. And other labs have shown that this mutation really is critical for receptor binding. And of course, and then that's the same mutation that's come in South Africa as well. And so that would be the molecular explanation for the higher viral load, which then explains the growth rate. So all those things kind of move together. So that's, and I think what they had to do in the UK is that because of they've had a very difficult epidemic, I think they felt they have to act sooner rather than later. And even though, not all the I's have been dotted and the T's have been crossed on the biology of this virus, it's important to act now to stop it spreading. So that was what made the UK government did what it did. Obviously, we're still now waiting a little bit on complete functional characterization,
right.
And we want to know exactly what's going on. I think the really interesting thing about both South Africa and the UK is that it's not just this one mutation, this 5.1 mutation, is that they actually have, those lineages have a huge number of changes compared to other ones, which is really fascinating. And there's one suggestion that's been going around, which actually makes a lot of sense, that they evolved in somebody who may be immunocompromised, and so then you've only got because you've got a chronic infection, much longer time in a single individual. You've got a partial kind of immune response there. And maybe that's allowed this virus to kind of evolve and select in an unusual way. So that's a very unique set of selective pressures on the virus in a patient like that's led to these changes. That's not proven by any means at all. It's an interesting theory. So
yeah, there have been a few cases of immunocompromise that show rapid evolution, so for your point there is well taken. The other question, Eddie, is, in the US, convalescent plasma is being used like, highly, without the evidence in hundreds of thousands of people now. Could that also lead to more evolution of the virus because they're getting these?
Well, it depends. I think it depends on the number of people being used relative in the proportion of the population. So selection is kind of numbers game. So it depends on there needs to be selection pressure for the virus to evolve in that way. So if the predominant if most people in the population were using convalescent plasma, then you would see a selection pressure. If it's only a small proportion, I don't think it would select that much. This case is different though, because it's in a single individual. And so in fact, you're replicating effectively, and a single individual has got a chronic infection. So what you're doing is replicating a whole population's worth of evolution in a single patient. That's why it's so unusual. And again, as you mentioned, in some other SARS-CoV-2 cases with the host immunocompromised, you see more mutations, as you also do in norovirus infections and influenza virus infections. I've seen that a few in my past work. So it's certainly a very interesting, theory. But this current variant, we need to monitor it closely. We need more on the basic functional biology. We need to see how the vaccines will cope with this. This is the kind of key question. That work's being done at the moment in the UK, I think. And fingers crossed that the vaccines are still going to be, tip top. And then if they are, we can breathe a small sigh of relief, I think.
Well, what do you think, though, in terms of let's say the vaccine is not resistant, the virus, of course, it's not a problem for this vaccine, but it shows you that while the virus was so slow in evolving in terms of any
Yeah.
meaningful functional variant, except for this
Yeah.
D614G that became the dominant one. Now we have a kind of different look at this
Yeah.
virus, and so does that make you think that even if it holds up, the current vaccines hold up well, that we're going to be looking at booster shots adjusted to the continued evolution of the virus for the years ahead?
Yeah. Yeah. It's a great question. So I think you need to think about evolution in different phases. So during the first phase, so basically most of this year, what you've had is a virus spreading in a population where there's no immunity. And that's been the key marker of this outbreak, really, is because everyone is susceptible. So in those circumstances, there's no immune pressure, no immune selection pressure on the virus whatsoever. And any lineage can find a susceptible host to infect. Anyone can. So it's actually really easy. So the virus just spreads and it just infects people. It's a kind of free for all. And there's no selection pressure. As immunity rises in the population, right, hopefully by vaccination, although some countries like the US and the UK are really trying hard to do this without vaccination, right? As immunity rises in the population, that's going to change the selective landscape, okay? And you will see evolution start, the virus will evolve away from that. I mean, that's an absolute racing certainty. Now, it does evolve a little bit more slowly than some RNA viruses, maybe 3 times more slow than influenza virus, but it's not abnormally low rate of evolution. It's actually pretty average, but lower than flu. So my guess is as immunity rises in the population, hopefully again by vaccination, you will start to see gradually immune escape. That will happen. That's an inevitable consequence of natural selection. It's been played out, from millennia, it's going to happen again. So eventually we will need, very likely, to update these vaccines at some point. Maybe that take 2 years or 5 years or 1 year, I don't know. But to me, it's a racing certainty that the immune selection pressure is going to push the virus in a certain way. And so you'll start to probably see more directed evolution than you have done in the past, okay? Because now it's harder for the virus to find a susceptible host because people are immune, right? And so only the fittest strain is going to make it through. And that fitness is going to depend on its particular antigenic configuration. So rising immunity will completely change the selection pressure. And I think it'll become even more seasonal too. I think early on, seasonality didn't need to be seasonal because there were so many susceptibles that any lineage can spread at any time. As immunity rises and susceptibles become fewer in the population, the right kind of conditions for spread become more important. So all those things will change. The virus will change in its behavior because of rising immunity.
Well, I mean, this is a central point you're making in that the race towards population level herd immunity, vaccine induced, is countered by the virus evolving. And we're not seeing the end of this virus just because you get 80% of whatever the world.
No.
Yeah. And
no,
so this is an endemic story, would you say?
Oh, totally. I would put money on this being an endemic respiratory virus. Absolutely. I don't think even if we roll out the best vaccine coverage program ever, we're not going to vaccinate everybody. We can't do it simultaneously. The virus will escape to it. I mean, it will evolve fast enough to keep itself going, and people will be and they'll re-enter the susceptible class. So no, I think it will become endemic. Absolutely.
Yeah. Well, that's exciting, isn't it? Well, it's kind of interesting to speak to a leading evolutionary virologist. You get a whole different perspective about because this is what you spend your whole life on, and you really understand, the context of what we're looking at right now.
I think it's also doing it comparatively as well, because I think people who are doing the evolution. I work on lots of different viruses, right, and I see the kind of try and see the kind of patterns between them, and and SARS-CoV-2 in a comparative way. I mean, it's not mysterious, right? It's not a magical virus. It has the standard properties that respiratory viruses do, and it's subject to the same rules of epidemiology and evolution, right? And they work pretty well, right? And I think we can make I can't predict what mutations will appear in what order at what time, but I think I can make a pretty sure prediction that it's going to evolve and it's going to escape immunity, like everything always does. So I think that's pretty safe, a pretty safe prediction.
Well, would you say it's fortunate that, that at least the spike protein gave it this ability to get a potent vaccine? Would you have predicted, for example, this whatever 95% efficacy?
No. I was confident. I was optimistic that not actually confident, silly word. I was optimistic that we get a vaccine. I was thinking more in the 60, maybe 70% if we were lucky. And
Right.
certainly not 95. 95 is absolutely spectacular, and more than once, right? Multiple vaccines seem to do the same thing. So and some months ago we did a little, I did an exercise, some people in the Wellcome Trust. It's very interesting on on horizon scanning. So playing out what the future might be in kind of 5-10 years to 10 years time. And we looked at vaccination and immunity and antivirals. And in our vaccine horizon scanning future predictions, a vaccine of this efficacy was our absolute best case scenario. I mean, right up there, right? So, and our middle case, most likely scenario was a lot worse. So I think in the vaccinations, we're in a very good place and incredible speed. So these people have done an amazing job.
Yeah, well, you helped them, you and Professor Zhang. Now, how do we get smarter for the next pandemic? We're going to have another one. Your friends, these viruses are going to haunt us in the future. How do we avoid, having the toll here of harm, of deaths and long COVID and everything else is profound.
Yeah.
How can we be smarter?
So I think there are three things we can do of increasing kind of difficulty. I think the simplest thing we need to try and do is somehow, and it's actually, when I say simple, it's actually not easy at all, but somehow distance ourselves more from the animal world. And I think there are clearly practices that we do today. So things like live animal markets, the wildlife trade, not zoning when we build on these wildlife areas where we're exposed. All those things, they increase our proximity to wildlife that carry viruses, some of which can infect us. So we need to be much smarter in how we regulate our exposure to the natural world, and that's quite a relatively easy thing to do. Just regulate more those practices. Second, we need much better. This is a very obvious thing. Much better global surveillance, and by that I mean I think the people who work at the human-animal interface, or live at the interface, they are the sentinels. They're the canaries in the coal mine, because they're going to get exposed more than anyone else. So for those sorts of people, maybe we'll need regular immunological screening, like something like VIR-Scan, a very cool technique. I've heard this global immunological observatory looking at blood samples globally. Maybe metagenomics occasionally of people who work, say, in abattoirs or live animal markets on a regular basis. And because they're the front line, they're like the fault line, the way I like to think in this kind of, even this earthquake analogy. They're where the tremors take place. So they need to be monitored really closely. And then that data has to be shared absolutely freely and quickly as possible globally. So there shouldn't be local governments holding on to it and saying we'll handle it ourselves. That is just that's a barrier to pandemic prevention. So surveillance at the front line, people animal human interface, rapid data sharing, and finally, and this is the difficult, this is I guess the Apollo project thing, is we need to have stockpiled in our freezers broad-acting antivirals and potentially vaccines that can recognize a whole span of coronaviruses or influenza viruses. So look, I'm not into prediction, but I think it's pretty obvious that there are a set of viruses that are particularly jumpy and that are likely to emerge in the future. And I would say the top three to me would be coronaviruses. This is number 5 in the last 20 years, coronavirus, right, in humans. So it's coronaviruses, influenza viruses, and paramyxoviruses seem to me the most likely to emerge. And so for those three, are there ways, this is a really big science project, that we can develop antivirals that can recognize multiple of these, or vaccines against multiple, and have those ready, rather than having to wait, even a year is really quick, but a year is time. Rather than having to wait for that, we have them there pretty much that we can roll out. So, and that's the real, that requires massive basic science investment. Okay. A lot of smart people working on it.
That's really helpful to kind of get a sense of what lurks ahead, particularly your ranking of the virus families that need a special attention. I love the concept of the broad preparation with antibodies and structure-based vaccines. That's that have that broad capability. Well,
so even now, sorry to interrupt, even now, I think in the coronaviruses, we know, if you look at the evolutionary tree of coronaviruses, you can see there are some lineages that appear like in the beta coronaviruses that jump most often. I think we know what they are. So I think we can certainly start to plan around, oh, they're the likely ones. Do they have any structural features in common that we can now utilize? So I think we can start on that now.
Yeah, no, excellent point. Well, I have to tell you, Andy, this has been a fascinating discussion. We hadn't met before, but to get your sense of the world is just invaluable. And having seen the historic tweet and some of the story is about what all happened back in January, and as well as some of your extraordinary work in the past. It's really a privilege to have this conversation with you. And any parting words of wisdom?
No, really, no. I think that not at all. It's a pleasure to talk to you because your the way you convey the message on Twitter for people to understand is absolutely invaluable. I think that's been a huge thing. In fact, I guess that does lead me to one of the things that I have noticed. I think that you're part of as well, in that the social media, its power in the pandemic has been absolutely amazing because it's so rapid, it's so immediate. And you can get your message out extremely quickly. Unfortunately, sometimes that's led to confusion, but normally it's been a phenomenal way of rapidly passing on what needs to be known. More efficient than the other standard channels that we've built since World War II to convey information about pandemics. It really has, okay? Yeah. And so I think for the future, another thing we need to do is we need to enhance those sorts of social media things. And because they are so direct, they're so rapid. And for this, and the pace that pandemics go, that has to be the way forward. We can't wait for these official committees to meet and have everyone sign off and so, because they are, I mean, valuable though they are, sometimes it's got to be quick. Right. And social media is just fantastically good at that. And that has been an absolute game changer too, I think.
Well, no question. The open science, as well as having that ability to get the word out through Twitter. And one other thing just to mention is the genomics community globally has really been, of all the different parts of life science that I'm familiar with, or medicine, the genomics community has really led the charge to be open like this. You have, of course, throughout your career. And now we saw how it paid off, because it could have taken a lot longer to get where we are in terms of a remedy. And so thank you for that. Thanks for the chance to visit with you. And I look forward to following you closely and checking in with you in the times ahead as we deal with this endemic mess.
My absolute pleasure, Eric. Absolute pleasure. Thank you so much.